My name is Andrew Jensen, and this is my pitch on acoustic emission monitoring and multi-axis damage localization in suspension bridge cables using distributed acoustic sensing. Kind of a lot, but I like it. So I don't know if you guys are familiar, but last year there was a suspension bridge failure in India, and 134 people died. This is a pedestrian bridge. It's not of the same scale that we see here in the Bay Area, but it is still a devastating event. 180 plus people were injured as well, and I know some families, or I heard of some families that lost 14 members in this one event. So it was really devastating for this whole community. So what happens in these suspension bridges is as they age, they corrode, they fatigue, and the bundles of steel wires that they're made up of for the main cables, they start to fracture and they fail. And as they fail, we can detect that as they age. So the problem is that a lot of these suspension bridges have a preference to being installed in humid or aquatic or semi-aquatic environments. Case being here in the Golden Gate Bridge, we have not only an aquatic environment, but a marine environment that is saline. So we get a lot of really bad corrosion in addition to large levels of humidity. This is all a very big problem for these cable jackets that are just kind of trap it in there and keep the humidity in place. It's very hard to inspect. Not only that, but these cable bundles are 3 feet in diameter. They have 27,000 strands in them. So understanding what's going on inside them is very hard to figure out via inspection. You can't really open it up too easily and drive wedges in there. You only get about 3 to 5% of the individual wires exposed in one inspection like that. So the Golden Gate Bridge has 34 full-time painters just to tackle this problem. Corrosion is a massive problem, and understanding it is a bigger one. So these bridges are very important, and it's important to understand what they're doing in order to keep them in use for generations to come. So the current standard uses piezoelectric sensors as kind of hit detectors, so they listen for the elastic stress waves that come from these wires as they fracture. They propagate along the cables. You can pick that up, hopefully, using a piezoelectric sensor. From there, you can determine what your feature of interest that you want to extract from these detected waveforms is. You can do hit counts and kind of monitor the rate at which these wires are failing. And from there, if you have well-calibrated piezoelectrics at the other end, you can determine where along the bridge these breaks are coming from. From there, you can investigate by hand. So what I propose changing is the first and fourth step. I propose using distributed acoustic sensing instead of piezoelectrics, and instead of longitudinal source localization, this would hopefully allow you to localize along the length, but also within the section. So it gives you three-dimensional information about where these breaks are occurring. So the question I want to ask is, can DAS, or distributed acoustic sensing, be used to increase wire break localization accuracy in suspension bridge cables? So distributed acoustic sensing uses fiber optic cables. A lot of you guys might be familiar with fiber Bragg ratings. This is different. It uses just the natural impurities present in the wire in the fiber optic cable itself. You lay it out in the field of interest. You attach it to this box, this black box called the interrogator. It pulses laser light down the cable. And from that, the way the fiber stretches as this laser light travels, it gives you strain rate measurements all along the fiber densely. So that is the advantage of DAS. You get a lot of sensor readings all along the cable, and it's very cheap. It's just a couple dollars per foot because it's just regular fiber optic cable. So the proposal is that we have a template acoustic emission waveform here on the top right in red. You pick that up on the sensor. From there, because of the dense sensor deployment, you can hopefully not only detect, because in my interview with the chief bridge engineer for the state of New York, he said that oftentimes when they open up the wires, they see fresh breaks that their current piezoelectrics didn't even detect. So hopefully we'd be able to pick that up using these because of the close proximity of the sensor to the wire break. In addition to that, you get a dense array of sensors, so you can localize along the bridge where these failures are happening using subarray beamforming approaches and particle filtering methods to estimate those source locations in 3 dimensions. So a quick summary would be, of this project would be to localize cable breaks in 3 dimensions, expanding it from 1 dimension, the current standard, to demonstrate the system's ability to be retrofit on existing structures, which is a very important point to keeping these structures in service for longer. The end product of this would be a volumetric heat map showing where these wire breaks are occurring with uncertainty measurements as well baked into there. So you can determine where, if there are any preferential locations within these cable bundles to fail, we'd understand where those are, and that can be used to ensure public safety through continuous monitoring as opposed to the every once a decade manual inspections that are incomplete, and also to identify preferential wire failure locations for future designs to improve them in the face of oncoming and continuous corrosion. Thank you.